Okay, so hello everyone. Welcome to the third integrable probability seminar. We are jointly holding this seminar with Safe Seminar from a Distance, which is hosted by Roger and Mariana here. Today we will have Kurt speaking from KTH, and he will be talking about multivariate normal approximation for traces of random unitary matrices. So I'll let you take the mic.
Okay, thanks a lot for the invitation and thanks for listening. So as Andrew said, the title of my talk is Multivariate Normal Approximation for Traces of Random Unitary Matrices. So this is, I should have written here on the first slide, all of what I will talk about is joint work with my former graduate student Gaultier Lambert. So, okay, now I have a problem. It doesn't, oh, now it works. Okay, so we look at random unitary matrices. So we just have the group UN of n by n unitary matrices with normalized Haar measures. So you have the uniform distribution, if you wish, on the group of unitary matrices. So this is one, as you know, one of the basic random matrix ensembles, also known as the circular unitary ensemble. So let me start with a little introduction and background to the problem, and then I will come to the result that we have here. So we look at the matrix U here from the unitary group, and it has eigenvalues on the unit circle with angles θ1 to θn. Right? So, and we look at a linear statistic of these eigenvalues. More particularly, we're interested in the traces here of powers of U. So we can group them together as we take the real and imaginary parts of the traces of U to the k with some coefficients. And then we have a square root of 2 over k is just a convenient normalization here. So as you can see, since the traces are sums over the eigenvalues to the power k, this becomes a linear statistic. So we have a sum of some function g of theta j, and g of theta is just this function that you see here. So throughout the talk, g will be this particular function here. And I can choose different coefficients here, xi 2k minus y and xi 2k here. So for the Haar measure, you can compute the eigenvalue probability density, and it's given by this Vandermonde determinant squared and some normalization. This is a so-called Weyl integration formula. So it's a classical result from the 20s. But since this is a product of pairs like this, as you know, this is also a Vandermonde determinant. So this is a product of two Vandermonde determinants also. And this leads immediately to use this and the Cauchy-Binet identity or Andreev's identity, you can see that if I take an expectation like this of a linear statistic, so this is, if you wish, a product also of the e to the g, then you see that this becomes a Toeplitz determinant also. So if you want to understand the statistical properties of this linear statistics, it's natural to look at its Laplace transform, so the expectation of e to this sum, right? And this is identical to this Toeplitz determinant. And from this, we can immediately get a result by combining this Weyl integration formula and the fact that this gives a Toeplitz determinant with the so-called strong Szego limit theorem, which gives is a classical asymptotic result for Toeplitz determinants. Now, so if we have this Toeplitz determinant here, and we assume that the mean of g is 0 on the unit circle, and that this expression here is finite, then the limit of this Toeplitz determinant as n goes to infinity is e to ag, where ag is this quadratic expression in the Fourier coefficients. So this is a classical result of Szego proved under somewhat stronger conditions in the early 1950s. And combining these results you see that we get immediately a central limit theorem type of result, or a Gaussian limit result for this linear statistic. So if we take the case M fixed here now, so then if I take the limit of, I can put an I here, so I look at the characteristic function sort of this Fourier transform of this random variable Z here. Then this follows immediately from the strong Szego limit theorem that this converges then to e to the minus psi norm of psi squared over 2 here. So this tells you that this linear statistic in the limit is a normal random variable. So this is sort of a prototype of this type of results throughout random matrix theory, that linear statistics of this form over eigenvalues converge to Gaussians in many cases. So now we will be sort of thinking about not just this sort of as a one sort of sum here, one random variable, rather to think of all the traces, the real and imaginary parts of the traces as sort of separate random variables. So I call them x2k minus 1 then for this normalized real part, and x2k for the normalized imaginary part of the trace. So this means that I actually get a vector of random variables here, x1 up to x2m. And of course, it's an immediate consequence of the result that I just told you about, that this also goes to a Gaussian vector here. So G1 to G2m, where the GIs are independent standard Gaussian random variables. And this is because I chose this normalization as square root of 2 over k. They become standard normal random variables. So this is sort of a vector convergence of these, a multivariate convergence of these traces then. This is sort of what you have in the title of the talk also. So this result is often attributed to Diaconis and Shashahani, who proved this without knowing about the strong Szego limit theorem in 1994 by a completely different method. So what Diaconis and Shashahani proved was that actually the joint moments of these real and imaginary parts of the traces are equal to those of the corresponding sort of moments of the Gaussians up to a very high order. So I haven't written the precise statement here. But so of course they cannot be all equal, because then they would be Gaussian, but up to a very high order, they are equal. And from this, you can also deduce this result here. So what Diaconis then conjecture, based on the fact that they are sort of the moments are really identical to those of the Gaussian up to a high order, that these random variables should actually be close. So this vector should maybe be close to the limiting vector, and also a linear statistic like this, at least for a fixed m here, should be very close to the Gaussian distribution. So more precisely, so Diaconis conjectured in 1994, that's when I learned about this conjecture, that this random variable, this linear statistics that we had, the sum of the g theta j, should actually converge super exponentially fast to a Gaussian random variable. So this in no way follows immediately from the fact that the moments are equal up to high order. But it's sort of, it's in a way, it may be still natural to conjecture that they should be very close. So I proved then a little later then that actually in total variation distance, then this random variable said here is very close to the normal random variable with variance psi squared. Then it's actually less than some constant times n to the minus delta n. So you really have a super exponentially fast convergence here in total variation norm. The constants here are not really explicit at all in my paper there. I mean, so I don't know how it depends, how they depend on m or the size or anything. So there's no control of that. I just prove that there are some constants. Of course, you could go through the proof, but if you did that, you would not get very good control of these constants. So that also means that if I go back to sort of look at the vector problem again, so recall that we looked at these real and imaginary parts of the traces, and we have this multivariate convergence also to a Gaussian. You cannot immediately say anything about the rate of convergence there. So Sarnak asked me a few years ago that if motivated by some problems in number theory, which I will not go into, if I could say something about the multivariate rate of convergence. And so give an estimate in total variation distance of how far the vector x is from the vector g. And particularly what happens if m is allowed to depend on m. So if I let m grow with n somehow, depend on m, so do I lose this fast rate of convergence quickly, or does it remain? So the goal of this project with Gaultier Lambert then has been to show a rate of convergence for this multivariate case, and also give sort of an estimate when m can depend on m, at least up to some size of m. And also another goal was to really sort of give explicit and not astronomical constants in the estimate. As I said, in the result I had before, there's really no control of the constants. Right? So we also aimed at actually keeping track of the constant and not making sure that they are not like 10 to the 100 or something like that. Okay, so here's the result. So there is, if you want to see more of the details here, there is a preprint from earlier this year where you can find details of everything I will be talking about today. So here, as you can see, it's an explicit statement. So for n greater than this 1911 and m greater than or equal to 3, and if I define this capital M to be the quotient of n over m, and this is sufficiently large. So if you read this, it means that m can be almost up to the square root of n, but not quite. Right? So almost up to square root of n. Then we have a bound in total variation distance between x and g, which has this form. So it looks pretty complicated, but you can see there is an explicit bound. And the important part that you should focus on, so think first of the case that m is constant, say that m is 3 or 4 or something. Then we would think that we have this super-exponential decay, and this comes from this 1 over the gamma function here, right? So this is sort of the important part of the estimate, that you, for a fixed m, you get this super-exponential rate of decay here. It's maybe a little hard to see what this estimate says when m depends on n. So to illustrate this a little, you can say that we take m to be some power of alpha. So m is n to the alpha with alpha less than a half. Right? And then sufficiently large. You could make this exact, precise also with this constant. So then you have a bound of this form. So you have something like almost, where epsilon is something that goes to 0. Right? So it's almost, but not quite, e to the minus n to the 1 minus alpha log n to the 1 minus alpha. So this epsilon n sort of takes care of the aspects of this here. And you can make it precise, of course, by analyzing what you actually have there. So as you can guess from this formula, it's a proof will be rather detailed, right? So what I plan to do now for the rest of the talk is not, of course, not to tell you exactly how I get 16 and all the details here, but to outline the sort of the structure and the main ideas of the proof there. But before I do that, maybe is there some question from anyone?
So do you not expect this thing to come, like the total variation between x and g, to have any bound of this sort if m is growing, say n to the 1/2 or slightly larger than that?
That's a good question. I don't know. I mean, the proof sort of breaks down when you go up to square root of m or higher, right? So then I can comment on that later also. But so the answer is we don't know, because we simply cannot go beyond that. It's quite difficult to get almost up to square root of n here. So, I mean, you could imagine that at some point there should be some change here where m really should start to affect the rate of decay. In a sense, this is not much worse than if I looked at a single trace somehow. I mean, it's a little worse, of course, but it's not that it's drastically changed. It still decays very quickly. And this was a disappointment for Peter Sarnak, because he really wanted that if m was not too large, this would have a big effect on the rate of convergence. But this is not the case here. So there could be a situation, there could be some m where this really starts to be important, that you're looking at a vector here, not just sort of a few traces.
Okay, thank you.
Can I ask one a little bit vague question? So there are results of the type that you take a unitary matrix, you cut, you look at the matrix element of this unitary matrix, and this will be Gaussian asymptotically. And then I think that maybe Mekas and Mekas or somebody else will discussing the case when you look kind of jointly on more and more of these individual matrix elements. And again, something was growing, like there were. Is it somehow connected? Because now you're looking at the powers instead of matrix elements, but is there any connection?
I don't think there is really any direct connection. It's sort of a different problem, right? Because, I mean, these traces are very special somehow, right? Because you have this fast rate to converge. As you say, there will be a breakdown also. When you take too many of these, it's not really close to Gaussian anymore. But as far as it's not directly related to this result. But it's nothing I've thought very much about. But. Okay, so now something is a problem again. Okay. So we can analyze this by, what we'll use is the characteristic functions. I take this vector xi, which is exactly the xi's we had before. So this is we have 2m of these numbers, right? And I look at the characteristic function, so the expectation of e to the xi dot x, right? And as we saw, we have different formulas for this, and this is important, right? We have one formula is this Toeplitz determinant. Another formula is this multiple integral, right? The Weyl integration formula. And the strong Szego theorem said that at least when m is fixed and n is large, this is close to the Gaussian characteristic function here, right? So the characteristic function of the vector g. So we somehow have to control this characteristic function that we have to control for all xi. Right? So if I let Pn of x here be the probability density function of this vector x of traces, then the total variation distance, this is the L1 distance, right, between this probability density and the probability density of the Gaussian here. Right? So since we want to use the Fourier transform, we start by considering the L2 distance instead, right? So we take the L2 distance between this probability density function and the Gaussian probability density function. And then, of course, by Parseval's identity, this is equal to the difference between the Fourier transforms squared. Right? So the right-hand side is what we have to analyze in order to understand the L2 distance. So if you start to think about this, and this is a split I also did in my previous work. So, but now we have to be much more precise and also think about really how things depend on m and all the detail, all the constants here, right? So you split this integral into 3 parts, right? So the first part is for when the psi is not too large here, right? So there is some lambda 1 that you have to choose appropriately depending on n and m here. And this is sort of the regime where you have the Gaussian approximation, where I expect that this characteristic function, just as we saw in the strong Szego limit theorem, is actually close to the Gaussian, right? So this I1 should be small because there is a good Gaussian approximation here. This should actually be the main term, right? Where you sort of see the true behavior, the true distance somehow.
But just to get some more, just to get a perspective on the initial problem, of course, C is just some arbitrary vector, right? But yes. You're saying, if I'm understanding correctly, the only real control, so April, you're not saying anything about the distribution of the x's, how they are growing or anything like that, but you're saying it in the, as far as the analysis is concerned, the only measure you need to control for the x's is their L2 values, xc mod xc squared. Am I understanding correctly?
Yeah, I mean, you want to control this integral, right? And you're integrating over all the i's here, right? So if you think about, if we go back and look at the integral formula, I mean, the psi is sitting here in the g's here, right? So you can, if psi is really large, this would be, this would be an oscillatory integral, and you will have some behavior, right? And what we sort of expect from this, the fact that the moments are close, like the Diaconis and Johansson, is that when psi are not too large, right? Then this little O1 here is actually very small, right? So you're close to this limit, right? But this cannot be true for all psi, right? Because of course, if it were true for all psi, it would be identically Gaussian. So this error will come in here at some point, right? So then this will have to be small for different reasons. That's why you sort of split this into these 3 parts here. So then there will be a sort of an intermediate regime, which is where you have to, so you split sort of the rest when psi starts to become large, you split it in one, which we call the intermediate regime, and one which is sort of a tail bound, which is when psi is really large here, right?
Okay.
And the reason for the split here is that you sort of use different ideas here and it's a priori, not, I mean, how you choose this split here depends on the kind of estimate you get there. And I will not be able to go into all the details there, right? But what I want to describe is what happen, what you do, sketch what you do in these 3 cases here.
Okay.
Okay, so let me start with a Gaussian approximation here now. So what we use there is the Borodino-Kunkel or Genormino case identity here now, which was discovered about 20 years ago now, right? Or earlier than that by Geronimo and Case, but sort of unnoticed, right? So that's the fact that this determinant here, the Szego limit theorem says that this determinant converges as n goes to infinity to e to the AF here. But you can actually write for finite m how much it differs from the limit, right? And this is given remarkably by this Fredholm determinant here. So this sort of captures in a way how far away you are from the limit, right? So the objects that you see here, so this is a Fredholm determinant on little L2 of the natural numbers. KF here is this product of 2 Hankel determinants here. So H plus is that you mean that you take the Fourier, H plus of some W, it means that you take the Fourier coefficients of W and you take the I plus J minus 1. This is a Hankel determinant, right? And if you take the negative Fourier coefficients, you get H minus. And you split the function F here in a sort of the positive Fourier coefficients and the negative Fourier coefficients. So that's the split here. So if you do that and put this into these Hankel determinants, take this product, you get this KF here. This is the operator that comes in. And then Qn is that you project onto this subspace here, which starts with n and then n plus 1 and all the rest, right? And of course, when n grows here, you sort of Qm projects to a smaller space, and if some regularity, this will go to 0, right? And you will go to the limit e to the af here. So this is the tool we want to use for this Gaussian approximation. Right? Because what you get, well, if I take now f to be ig here, right? So then if we go back, then if I take ig here, this was exactly the Fourier transform, the characteristic function, right? So this is this e to the aig, right? And then you take the difference between this and the characteristic function for the Gaussian, right? So then of course you have this Gaussian factor, and then I get the determinant minus 1, right? So of course this will then go to 0, right, when n goes to infinity if m is fixed here. But now I want to estimate the difference between this Fredholm determinant and 1. And this you can do by a standard estimate in terms of the trace norm of this operator. So you get the trace norm of the operator times e times 1 plus the trace norm. So this is a standard estimate that you can find in books on trace class operators. And the trace norm, recall that, if I go back one page, recall that this operator was the product of two Hankel determinants. So this means that the trace norm of this is sort of, can be estimated by the Hilbert-Schmidt norms of these two factors here, right? So what I need to control to estimate this are the Hilbert-Schmidt norms of these Hankel operators. So at this point, you just have to sit down and compute now. We know what G is. I can compute what this object here is. I compute the Fourier coefficient, but note that I cut off with Qn's. I only compute the high Fourier coefficients here, right? And estimate the norm of that, right? The Hilbert-Schmidt norm. And this you can do, and with some work with, will not show you. If you're interested, you can look in the paper, right? But this is sort of straightforward, right? You just estimate the Fourier coefficient. You have to think a little how to do that, but it's pretty straightforward. And with some work, then you end up with this estimate here of the norm. And this here you see this, what was the important factor in a way in the final estimate. This is where it comes from. So if m was fixed, as I said, this is a super exponentially small here, right? Rho here is where the psi dependence come in. So rho is this number here, right? It's square root of 1 plus log m over 2 times the norm of psi. And this bound, of course, cannot be valid for all psi, right? Because when psi is really large, you start to get these oscillations, and there is no reason for this norm to be small anymore, right? So there is this rho, which then is more or less normal psi, should be less than n over m, or this capital N. So this up to that bound, this thing here, you have a control for those psi. So not for all psi, but for those psi, we have a very good control of this. And we know how close this transform is to the Gaussian. Right? So this is the control you have in the Gaussian approximation part here. The other parts now, we really want to be small. Right? So let's turn to this intermediate regime now. So then we use the other formula, the characteristic function here is also given by this integral, right? So this here I've just rewritten this fundamental determinant, the absolute value e to the I theta k minus e to the I theta j. You can rewrite that as sine squares instead, right? So this is just some trigonometry. Right? What you see when you write it this way is that this integral is actually an analytic function, right, in all the variables. Right? So it means that you can do contour deformations here now. So I can do the following. I change variables. So I do a deformation of sort of the contour of integration into the complex plane. Right? So I make this change of variables and I can deform the contour back to the interval minus pi to pi again. So if you do that and put in sort of estimate, no. So now we don't want to prove that this is close to the Gaussian now. We want just to prove that it's small, right? So that the contribution from this intermediate regime is small. So you see here, I just introduced this change of variables into this sine squared part here, right? And I've also taken out the sine squared part again and written so that I can write the expectation again. Right? This part here comes from, you get a contribution from the Jacobian when you change variables, right? Which is estimated here. And here you sort of just introduce this change of variable into the G function here and taking the absolute value. So we have this bound, right? And the idea is now to choose H in a good way and try to estimate the right-hand side. So nu here is some parameter that we can play with, right? To choose it appropriately so that we, in the end, get a good bound. So that's a freedom that we have. We can choose H and we can choose nu, right? So you can simplify this a little and estimate sort of, I mean, this is rather complicated. You can see that you can estimate it essentially by, you take this H theta minus H phi squared over this sign difference here squared. This is sort of the square of this part. So this is what comes out as a double sum. This is what comes out if you start to expand here. And then, of course, there are error terms, right, which you get, right, but which you also have to estimate. But these are sort of the main things here. So this is a positive quantity, but this is something that should be, so give sort of a negative contribution and make this small by a good choice of H here. And then you hope that the error terms should be negligible then, or small compared to the other thing here. So it turns out that the good choice here is to choose H to be the conjugate function of G. So you sort of change sines and cosines, right? So the Fourier coefficients of HK is minus I sine of K times the Fourier coefficients of G, right? This is sort of, if you look at it, if you would take sort of the integral of this, you place the sum by integrals over the thetas. This is sort of what would minimize, make this as negative as possible. So it's a good choice in that way. So you make this choice here of H, and then we want to estimate this expectation. So now there's a nice fact that you can use here. If you have a linear statistic, you know that this thing here is again a linear statistic. It's just the sum of the eigenvalues, right? And if you have a linear statistic, so a trace of some function of u here, the expectation of that, which was this Toeplitz determinant, this sort of goes to this e to the AF by the strong Szego limit theorem again, right? But it's actually, for a real valued f with mean 0, this is actually an upper bound also. So it actually increases towards its limit. So this you can see, if I go back, this you can actually see also from this Borodin-Okunkov-Jerome case identity. It's just because this Fredholm determinant is actually less than or equal to 1. I should also mention, I forgot to say that these Diaconis-Shashahani identities actually follow from this, because sometimes this operator is actually identically 0. So you actually are equal to, you have an exact formula for the Toeplitz determinant. And this you can use to prove these Diaconis-Shashahani identities also. So they sort of, in a way, they're sitting in this. And this is also, maybe if I go back again, since this is an integrable probability seminar, this is sort of in a way where integral probability in some sense comes in also, because this identity is sort of comes out of sure measures and such things, right? So there is some sort of deep thing behind this also in terms of integrability. Okay, that was a remark. So let's go back to trying to understand this intermediate regime and estimating this expectation. So using this, if I have a linear statistic, so a term like this, I can estimate this. I mean, I could split this into different parts using Cauchy-Schwarz, right? And then something like this I could estimate using this and would give quite a good bound, right? However, here I have also, this is a double sum, right? What you could do there, of course, you can see how large can this be. If you look at this quotient here, you see that you could bound this by the infinity norm of h prime here, right? And if you use that bound, you could get this m to be almost the cube root of n, but not all the way up to square root of m, or almost square root of m that we had in the theorem. So we actually try to not use this straightforward bound, but maybe a little more precise. And the idea, which I will just sort of indicate here now, is the following, that we know something for linear statistics. For those, we have a good bound. So we somehow want to linearize this quadratic, e to this quadratic expression, right? Because if I let tk be these traces, which are linear statistics, right? Then a computation which you can do with this function h, you recall that h was this thing, capital H was this quotient squared here. If you work a little with that, you can see that you can expand this as a quadratic form in these traces with some coefficients here. So this is just, again, just trigonometric identities that you use here. So now, you know, if you have e to some quadratic form, at least e to some positive definite quadratic form, you could write that as a Gaussian integral and sort of linearize the quadratic form in a sense. This need not be positive definite, but you could bound this with some positive definite quadratic form in these traces and their conjugate. I'm not saying the details here because it would be a little involved, but if you have something like that, then e to this positive quadratic form, you could write then as a Gaussian integral in this way. So a multidimensional Gaussian integral, where m would then come from, of course, from this quadratic form here. But then it would be something linear in these t pieces. So this psi z of e to the I theta j depends on z here and z bar here, but in a linear way, right? And it's a linear statistic now. So if I take the expectation now of this object, I can take the expectation inside and take the expectation over the unitary group now of this object. And again, I could use this bound here. So then I will get something quadratic in the z, but I can compute, it's still a Gaussian integral, and I compute it and I get some estimate. So there are lots of steps to be carried through there, but if you do that, you actually get a better bound. And this is what allows us to go almost to square root of n here, to control things for m almost as large as square root of n. So this is one case where this condition actually on that m is not too large, not great, little smaller than square root of n comes in here to have a good control here. So of course I'm leaving out all the details here now, but in the end you get some bound like this, which is sort of smaller than the bound you got from this Gaussian approximation. So we want this to be at least not larger than the bound we got from the Gaussian approximation. And there is a split here with another lambda 2 here into two parts here. But this means that we now, if we go back to this split that we had, we control the Gaussian approximation, we know how to do the intermediate regime. But from the intermediate regime, if I go back, you see this is bounded by something which is very small, but it doesn't decay with xi, right? So I cannot use this all the way to infinity in xi, right? It doesn't give me anything for really large xi. So that's why I need a tail bound also. I need to do something else for xi really large here. So that's sort of the remaining part here. So we need a bound for xi large here. So what you do is that you use the same change of variables idea. So if I go back here, we have this estimate here, right? And then I made a choice of age here to be this conjugate function. But I could look at this and choose another age here. And it turns out that another good choice is to take h equals to g prime here. And if you start with that, again, this bound that came out from the change of variables and work with that. So now I'm skipping lots of details. You can end up with a bound like this here. So you have e to something here and a linear statistic again here. But it's a linear statistic in g prime theta squared. So you see at least this is negative. So this could potentially give you something small. Aha, okay, maybe we use the same estimate again that we had in the sort of Szego theorem here, that it increases to its bound. But that would not give a good bound here. I mean, that's sort of useless for xi large. So we have to do something else here. So we have this integral here, right? And we have this linear statistic here. So we're interested in this particular case, right? So we have to estimate this in some other way, right? So what we do now is somehow when xi is really, think of f as really large here and really, then actually this is sort of the important thing, not really this. Usually think of this fundamental determinant squared as the dominant part, the really important thing, right? But if f is huge, then maybe this is not so important, right? So I could just take an upper bound on this. So this is always less than n to the n here, right? This is equality when you have an equidistant points on the unit circle, right? Like a regular n goal, right? So if you just replace this by n to the n, then we get this bound of the expectation here. So then you just get a product of single integrals, right? So we get this integral to the power n, and we get n to the n over n factorial, and with sort of a Stirling bound, you get this factor here. So then we reduce the problem to estimating this one-dimensional integral here, where we can use other techniques. So the estimate that we use now to estimate this single integral, you can prove that it's smaller than this object here. So let me not go into the proof. You can have a look in the paper if you're interested. This requires some thought, but okay, take the case where say g prime of theta was equal to theta. So you can see what's the problem with the problem. So think of gamma is something large here, right? What if g prime has a 0 here? Then it's not so good, right? But even if gamma is large, then you would still not have a small integral. Like, of course, this would happen in a relatively short interval, but still you have to sort of estimate this effect, right? So if I have a simple zero, then g prime theta would sort of be like theta squared around that zero. Say I have a zero at the origin, then this would be like theta squared, and I could sort of have sort of like a Gaussian integral. But g prime theta square is a trigonometric polynomial of degree 2m. So potentially it could have a zero of degree 2m. Of course, that's very unlikely to happen, but it could happen. I cannot exclude this. So if I want a uniform bound now for all choices of psi here, now for some choices of psi, I could have a zero of order 2m. So therefore, I get this rather slow decay. I get this 1/4 to the m. That sort of comes from a sort of a worst case that I could have in this integral here. But anyway, using this bound and using it to estimate this expectation here, I get a decay like this. That the characteristic function decays like 1/xi to the power n/4 here, where n, remember, was this small n, the size of a unitary matrix, divided by m, the number of traces we're looking at. And I have an explicit C and M here, of course, which I haven't written down here. So this is good enough to control this tail here. But actually, if you look at the bound and compute this tail integral, you see that here also you need actually that m is smaller than square root of n. So we don't actually have a tail bound that is good enough when m is really large. So this is another point where this condition comes in. So I cannot with these techniques really go beyond this square root of n here. But now, maybe I haven't convinced you, but I've actually at least indicated the types of ideas that comes into these three regimes here. So for the Gaussian approximation, we use this exact identity, right? The Borodino-Kunkov identity. In the intermediate regime, we use this change of variables with a good choice, right? And in a way similar for the tail bound, but here also we reduced it to a one-dimensional integral. So now what remains is, of course, you have to combine all these estimates, right? And choose this splitting in a good way so that you sort of optimize things and also optimize how the constants work in all these estimates. And this is, as you can see, if you look at the paper, it's a lot of detailed work, which is complicated to do. But I mean, once you have the bounds, you can work with it. But it's actually relatively subtle if you want good constants here to combine all these things in a good way. So this was an estimate for the L2 norm. So of course, we want to go to the L1 norm in the end. So let me not, this is sort of a standard idea how you can do this. So the idea is that this is the L1 norm, right? Recall this was the density function for this vector of traces, right? And this is the density function for the Gaussian vector. So I split this integral over the whole space R to M into one sort of bounded part here between some L that I have, minus L and L to power 2M, which I have to choose, where I have to choose L, right? And then the complementary part, right? For the complementary part, I can sort of, I just take each term here, take the, and then so this part will then be the probability that this vector lies outside this box, right? And this again, if I take L large, I can control this using this bound that we had. Again, recall that the Toeplitz determinant increased to its limit, which gave me a bound, right? I can use this bound and Markov's inequality to estimate the probability that the vector is outside this box and prove that it's small. And of course, I can estimate the Gaussian integral outside this box also, right? And for the first part here, I just use Cauchy-Schwarz inequality and then use the L2 bound, right? So this is where all work that I just talked about comes in. And then you combine these and optimize over L to get the final result. So these are the structure of the proofs here. And I hope I've given you some indication of what comes into the results. I think I actually stop here and see if there are any questions. So thank you very much for your attention.
Okay, let's all thank Kurt for a wonderful talk. Are there any questions?
Yeah, I'd like, I have a question. I don't know if it's a fair question in any way, but the approach which you've outlined here in such an expert way is an analytical approach. Basic problem is